Today we're going to work on our notes for 2.6 rational functions, day 1. So it's important to know that a rational function can be defined as r of x is our rational function, as p of x over q of x, where p of x and q of x are polynomial functions. So here's a first example of a rational function. So I have the rational function f of x equals 2 times the quantity x plus 5 times the quantity x minus 3 over the quantity x plus 1 times the quantity x minus 3. Our top function is a polynomial function, like we studied in the last section. Our bottom function is also a polynomial function, like we studied in the last section. So here is the graph of this function f of x. So a couple of things to notice. The solid lines are the solutions and part of our graph. The dotted lines are asymptotes. Asymptotes are lines that the function gets very close to but does not touch. Okay, so as the graph gets close to this line, x equals -1, it gets closer and closer but doesn't touch. Similarly, this horizontal line, y equals 2, the graph is getting closer and closer, but it doesn't touch. This is something that you've probably never seen before. This is called a hole in the graph. Okay, so we represent it with an open circle, and it shows a discontinuity in the graph. Continuous means that you can, sort of the layman's version of continuous is that you can draw the function without picking up your pencil. Discontinuity means there's a break. You have to pick up your pencil to get from one part of the graph to the next. So on this graph, we want to talk about a few things. So we have a vertical asymptote at our line x equals -1. Okay, remember this is the equation of a vertical line. X equals a number. From the graph, I can see that this is x is -1. I have a horizontal asymptote, so that's this dotted line. Again, these dotted lines are drawn in to show behavior of the graph, but they are not part of the actual graph. Okay, but we do draw them in to give more information about the graph. So our horizontal asymptote is at y equals 2. Looking at my graph, I can see I have a hole at the point 3, 4. So my domain is going to be any value that x can be without breaking the function. In my range, any x values, and my range are my y values. So looking at this graph, I can see starting at -infinity, right? This graph continues in this direction. I should draw arrows. Desmos doesn't do that for me. Okay, so I can see that I start at -infinity, and then I can see that -1 is not included. So I have an open parenthesis there. And then I start up right after -1, and my x values go all the way to infinity. Similarly, for my range, I see that I have values starting at -infinity and going up until 2. 2 is not included because my graph gets closer and closer to a y value of 2, but doesn't touch. And then I start up again at 2 and go to infinity. So on the previous page, we talked about what a rational function looks like, and we saw the graph and identified the different pieces. Now we want to talk about how we can graph a rational function on our own. So we are going to consider the rational function f of x. And the first step when graphing the rational function is to factor the numerator and the denominator. So pause the video now and factor the numerator and the denominator of f of x. Okay, so I got that the numerator factored into x plus 3 times x plus 1, and the denominator factored into x plus 3 times x minus 1. I am noticing that I have the same factor, x plus 3, in the numerator and the denominator, so that means I can divide out my factor of x plus 3. Okay, so x plus 1 over x minus 1 is an equivalent fraction, equivalent rational expression to my f of x. So next, I want to use the factors in the denominator to determine if there are wholes or vertical asymptotes. If the same factor occurs in the numerator and the denominator, there will be a whole at the value of x that makes the factor equal to 0. You're going to substitute the value of x into the reduced function. Okay, this is important, the reduced function, to find the y value and list the whole as a point. So I can see that the factor x plus 3 occurs in the numerator and the denominator. So I'm going to have a whole at the value that makes x plus 3 equal to 0. Solving that, I get x equals negative 3. If I was going to plug this into my original function, I would get negative 3 plus 3 would be 0. I would have division by 0 in the denominator. So that's why instead of looking at the original function, I'm going to look at the reduced function. So I am going to evaluate f of negative 3. So I get negative 3 plus 1 over negative 3 minus 1. So this becomes negative 2 over negative 4, which is 1/2. So my whole occurs at the point negative 3, 1/2. Okay, so anytime you're giving a whole, you want to make sure you have it as a point, okay, with its x coordinate and its y coordinate. If a factor occurs only in the denominator, there will be a vertical asymptote at the value of x that makes the factor equal to 0. The vertical asymptote should be represented as the equation of a vertical line, that is, x equals a, where a is a real number. Then we want to determine if the function goes to infinity or negative infinity to the left and right of the vertical asymptote. Okay, so I'm looking at my function. I see the factor x minus 1 only appears in the denominator. So I'm going to have a vertical asymptote. I'm going to abbreviate that as VA for vertical asymptote. When the factor x minus 1 equals 0. So solving for x, that's going to occur at the line x equals 1. Now, to determine what happens on the left and the right of 1, a rational function to the left or right of a vertical asymptote is either going to go to infinity or negative infinity. Those are the only choices. So what we can do is we can think about x as it approaches 1 from the left. This indicator with a minus means 1 to the left. So I want to think about a number that is a little to the left of 1. So I am going to think of the number 0.9. Okay, so if I take 0.9 plus 1 and I divide it by 0.9 minus 1, I can see that I have a positive number divided by a negative number, okay? Which means positive divided by negative means I'm going negative, and my only choice is positive infinity or negative infinity, so that means I'm going to negative infinity. Similarly, if I think about x to the right of 1, okay, so this indicator means 1 to the right. This time, I'm thinking about a number like 1.1. Okay, and all I'm doing here is, I should have explained this, is plugging into this reduced function. Okay, so x plus 1 and x minus 1. So I let my x be 1.1. In this one, I let my x be 0.9 on this one. So 1.1 plus 1 is going to be positive. 1.1 minus 1 is also going to be positive. Again, my only choices are positive infinity or negative infinity. Because a positive divided by a positive is positive, this is going to positive infinity. You can either write the plus infinity or you can just write infinity. There is a whole or a vertical asymptote at an x value. A whole and vertical asymptote cannot occur at the same time, okay? They can't be simultaneous. A rational function can exist without a vertical asymptote or whole. In this case, you would write none, okay? If you were asked, what is the whole, what is the vertical asymptote? As a rule, a function cannot cross a vertical asymptote. At this time, we can also determine the domain of the function. The domain of a rational function will be all real numbers, excluding the x values where vertical asymptotes or wholes occur, since these values make the function undefined. Okay, so again, looking up here, I can see x equals -3 and x equals 1 is going to make my function undefined. So a couple different ways to write this. The first is in roster notation. So I'm thinking about my x, and x is going to be an element of the real numbers, but x cannot equal -3 and x cannot equal 1. Okay, so this would be our domain in roster form, and my domain in interval form or interval notation. I am going from negative infinity. I have a problem at 3, so 3 cannot be included. I can start up again right after 3, -3. I have another problem at 1. 1 is not included. And then I go from 1 to infinity. Okay, so my rational function has 3 separate intervals that are included in the domain.